Okay, good afternoon, everyone. Let's start the next session. We will have 3 20 minutes each talks in this session. The first one is by Jahns, no, Joscha N.
Yes.
And yeah, all to you. He's going to talk about a couple of highly scattered FRBs found using CRACO.
Yeah. Yes, thank you. And hi, everyone. I'm Joscha Jahns-Schindler. I'm a postdoc at Swinburne University working with the CRAFT collaboration. I will be talking about the ASCAP telescope, about our new CRAFT backend, and about one highly scattered FRB that we found with it. So before I start, I want to say thank you, everyone. Thank you to the organizers for organizing such a fantastic conference. And thank you for everyone else taking good care of me, taking me around the city. It has been tremendous fun. Learned a lot besides Fast Transients about the Indian culture and religions and everything, the food. So thank you. And let's start with the takeaway points before everyone falls into the post-lunch sleepiness. So the summary of the talk is that the new backend, the new coherent search system is working, and it's finding all kinds of interesting sources, especially long sources and scattered FRBs. We found one highly scattered FRB that shows that high DM and scattering is possible even from the circumsource medium alone, because we will discuss it more. And finally, it shows that there exists a population of not so fast FRBs, and it's been great to hear that some other surveys are also searching for these now. Let me start from the beginning. So we already heard quickly something about ASCAP. It's not the most sensitive telescope, consisting of 36 12-meter dishes, but its superpower is this phased array feed that has a very wide field of view of 31 square degrees, which gives us a really good FRB detection rate. And of course, it's an interferometer, and so we can localize the FRBs. So several surveys have been conducted over the past years with this telescope. The first one was the Flies Eye surveys, which was conducted when the telescope was still under construction. And basically, they used 8 to 12 dishes to just point to random positions in the sky to make a very shallow survey of the southern sky. And it was very successful, finding 20 FRBs in a very short time. But now we are running fully commensally because other people want to use the telescope as well. And this was done in the last years with the incoherent sum survey, just summing the beams incoherently. This found 43 FRBs. And some of the highlights I put here, like the first localization of a non-repeater, and also like I think the second localization of an FRB at all. Then the sense of baryons, of course, from 2020, and many more, like host galaxy studies and polarization studies, as you heard from Apurva. So yeah, a lot of it is summarized in Shen et al. 2024. So now we have commissioned the CRACO backend, the CRAFT coherent backend. And we are now searching in the time domain as well, coherently. And that means we form images in all the 36 beams over 280 DM trials with 256 times 256 pixels. We cut a few of the outer antennas to save some computing power and be more efficient, sacrificing a little bit of sensitivity. Yeah, our time resolution we are currently searching at is 14 milliseconds, although we can actually go down to a quarter of that. The reason we don't go down, or we went up again, kind of, is that the ICS survey is also still running in parallel, and a lot of the sources we found were found in both systems. So to span a larger parameter space, we changed back to 14 milliseconds to find some longer sources. Right. So some of the things we found so far are especially long duration sources. So this is especially well possible with these instruments. And the other thing that is possible that you can search all the way down to 0 dm. So you can also find very low dm things. So one of our LPTs was very interesting because we also found X-ray emission with it, and so therefore showed that it's probably a magnetar. Another LPD had interpulses very similar to pulsars. Then we found one very long pulsar, 41 seconds, kind of in between the long period sources and the pulsars. And then we also found a nanosecond pulse from a dead satellite. So this was the one that's actually found at 0 dm. And yeah, I think it was especially interesting for the satellite community. So these low DMs also give us a handle on the galactic sources. So we also found 10 new AREDs. But now I'm like done throwing all things at you. I want to focus on one thing now, which is the scattered FRB that we found. And first I want to motivate why we are searching for scattered, or why scattered events are interesting. So there's 3 points mainly. Scattering, first of all, makes detections more difficult and therefore causes biases. So we have to study it and correct for it when we do cosmology. Yeah, so that's making it difficult, and we need to learn more about it. And secondly, it could also be possible that we can use this, the scattering to constrain the dispersion measure. So for pulsars, we have this nice relation in the Milky Way between scattering and dispersion measure. And if a similar relation would exist for FRBs, it would be great. We don't expect it to be this tight because we have always the same point. We are always at the same point in the Milky Way, and other galaxies might also be more turbulent, have more gas or something like this. So it's probably not as stringent, but if we find any correlation between the scattering and DM, it would be great because we could lower our uncertainty on DM host. All right, and then lastly, we can also use it to constrain the turbulence in intervening halos. So this FRB that was in the background here skewed one of the foreground halos, and you can put constraints on the scattering or on the turbulence in the CGM of this foreground galaxy. Okay, let's come to the FRB that we actually found. So this is what we found, and you can very prominently see two effects that we learned about last week, two propagation effects, which are scattering and scintillation. So scattering is, we know, is this long elongated tail here, and scintillation is the patchiness in the spectrum. And this patchiness is from the interference of different images arriving at our telescope. And the tail is from the different path waves having different path lengths. And so part of the images arrive later, therefore causing this exponential tail. Yeah, so the two are related as well. So the scattering time usually is 1/2 pi times the scintillation bandwidth. But in this case, it doesn't match at all. So in this case, the scintillation bandwidth is much larger than we would expect. And therefore, we probably have two different screens here. And our interpretation is that the scintillation is caused from the Milky Way screen because it is consistent with the Milky Way models. And the scattering is much larger than expected from the Milky Way at this high latitude sightline. And therefore, that is probably from the host galaxy. And we can also actually put a number on this because we learned last week that to get scintillation, the source must appear as a point source to the scattering screen, or to the scintillation screen in this case. And so that because we see the scintillation at all means that we can put a constraint on the product of distances here. And it is a very good constraint because of the high scattering. We can assume that the Milky Way screen is probably at around kiloparsec distance, and that would put the host source distance, so the distance between the source and the host scattering screen, to about 8 parsec, which is amazing. All right. So what could cause such such a high scattering is the question now, right? We have luckily the FRB is very close. It's at 0.05 redshift only. And that means we can see the host galaxy very precisely. Normally, if we see such a high scattering, people say, okay, it might be from the center of the galaxy somewhere, and there you can get very high scattering. But in this case, it comes from a spiral arm, so there's no reason to be such high scattering. We can also not see any counterparts for it, neither an optical, infrared, or radio, so no PRS as well. Right, so we can also see that the inclination is very low, so it's almost phase on. So there's also not much disk that the FRB could have gone through. So we can compare it with the Milky Way. So this is these are all the Milky Way pulsars. So in the Milky Way, and this is the FRB at the inclination of the host galaxy. So the only way where we can see a similar scattering is at the through a lot of the Milky Way disk, and even there only towards the center of the galaxy. Right, and the host TM on the other hand can also be very good constraint because of the close distance. And that one is slightly higher, or it is a lot higher than expected at this inclination, but not quite as outstanding, I guess. Okay, so the question is now, what can cause this? We don't see anything. It cannot be the ISM kind of. So we can already argue that it is the only plausible argument is that that it is the circumsource medium. All right. So now, first of all, we need to think about what is causing scattering at all. So there's two competing theories. One is diffractive and one is refractive scattering. In diffractive scattering, you have turbulence and an extended screen, and this turbulence is causing the wave to wiggle, for lack of a better word, and therefore you get an arrival from different angles at the observer. Refractive scintillation, the biggest difference is that you have a sharper screen, a very thin screen, and usually larger clouds. You can think of it as an ensemble of plasma lenses that is doing the refraction. All right, so the first one has been the classic way of explaining pulsar scintillation and scattering, while the second one came up more in the last 20 years, I think, with the detection of these parabolic arcs in pulsar scintillation, which argue for a thin screen. All right, in our case, we can't really say because it's very difficult from only the scattering to say what is causing it. So I calculated both for both cases. For diffractive scintillation, you can, or diffractive scattering, you can have a direct relation between the size, the characteristic size that is causing the diffraction, and the angle of the scattering. And so that's only 500 meters here, which is incredible for astrophysical time, length scales. And this is commonly related to, like, the question is what causes turbulence, on what length scales do we expect turbulence? And usually people invoke the ion inertial scale. And in this case, that would imply densities of 2 × 10⁵ particles per centimeter. Yeah, if we combine that with a DM, this yields, for example, a supernova remnant, and the supernova should have happened only less than a year ago. In which case we should have probably seen it. So the other theory, refractive scintillation, you can only say something about the gradient of the dispersion measure perpendicular to your line of sight. So in this case, you would expect a dispersion measure gradient of about 9 parsec per centimeter cubed per astronomical unit here. So this is also a lot, and also would require a density of, I think I calculated 2 × 10⁶ particles per centimeter, so even higher. In both cases, we expect a very high density medium. All right, so what are possible sources? Things that came to mind are a supernova remnant maybe, but as I said, it has to be very young. an H2 region would be possible, but in any of the H2 regions in the Milky Way, we don't see any such high scattering. So that one we can kind of exclude. Another possibility would be an offset black hole. So something similar to the center of the Milky Way, but somehow the offset is, the black hole is offset and possibly due to a merger with another galaxy. But that's all speculation, kind of. So fourth possibility would be that it is similar to a PRS, whatever is causing the PRS. We don't really know. So in that case, we can compare with different FRBs. 121102, for example, the PRS would have to be 70 times fainter than the 121102-1 because we took images with ATCA and found nothing. Yeah, compared to 1905-20b, it would have to be even fainter. All right, let me come to the end. So in summary, again, we found this very scattering. No, first of all, the new search system, CRACO, is working and it is finding very interesting things, especially long transients and scattered FRBs. Our highly scattered FRB shows that you can have very high DM and scattering from only the circumsource medium without invoking the host ISM. And it also shows that there exists a large population of not so fast FRBs. And you can actually see, or the error bars are large, but we don't see any decline in the rate of FRBs in temporal log space. So it is worth looking for longer transients. And I'm very happy to hear that several other people have also said that they would be looking into it more. So thank you all for listening.
Thank you, sir. Questions, comments?
So just to clarify, what was the scattering time? Is it about 1 second based on this?
700 milliseconds.
Okay.
At 700 milliseconds at 800 megahertz and 300 milliseconds at 1 gigahertz.
And then just about the interpretation, if it's a supernova remnant with a year, or I mean, with an age of a year or less, the region would be extremely opaque to induced Compton. So it will be very difficult for the FRB to escape such a region. I think it might be useful to try and think of other interpretations that don't require something so young. And yeah, I mean, even any kind of PRS or something like that would be extremely light at that point as well.
Yeah, I think the way that we found it would be possible if the PRS is younger than the other ones that we see, because at the beginning the PRS gets brighter with the expanding.
Yeah, it does get brighter depending on your favorite model for the PRS. If it's, we can talk about it maybe later, but if it's rotation powered, as you'd expect for sort of pulsar-like system as opposed to magnetar, then the peak emission will actually be on this kind of time scale. Because later on you have adiabatic cooling that gets rid of most of the energy. But either way, you have the problem of the opaqueness. So the FRB itself will not be able to escape such a region.
Okay.
So anyway, it's something to think about, and certainly a very interesting observation. Thank you.
Thank you.
Nice talk. I was just wondering about the motivation slide that you put, where we would love to have a Taudian relationship between FRB hosts and for FRB hosts, but realistically, do you think that will ever happen, given that DM host will always remain uncertain for sources where we basically don't have any foreground information, and even if we do, then like there's going to be some scatter from the Milky Way.
Yeah, so this is something we have to learn from burst C, basically. We need very close by FRBs where we can see exactly, like in this one, where in the host it came from and what is there. And where we don't have any IgM in the middle, where we don't have any intervening galaxies. And so we can know quite precisely. So for this one, the DM constraint on the host that I got was 140 plus minus 50, I think. So still a large error bar, but you can say much more than for most other FRBs.
Any more questions? If there are any questions from Zoom participants, please unmute yourself. Okay, let me ask the last question then. You mentioned you guys do 480 steps of DM trials.
280, I think.
280.
Yeah.
So does that limit the DM range you can explore?
Yes, it does. So we are using the FDMT, fast DM transform. And that means you always have a fixed correlation between the maximum DM and your channel width and time. So it depends on the band. ASCAP is observing at 3 different bands as well, and it depends on the band how large the DM is. And I don't have it in my head right now. Yeah.
Okay, thank you. Okay, if there are no further questions, let us thank the speaker again.